student receives test scores of 62, 83, and 91. So these are the tests. The term project score is 88. Homework was 76. Okay, and then it tells us that tests are each 20%. The project is 25%, and the homework is 15%. So how do we find our final score? So for a weighted average, we have to add all these up, but we have to take them times their weights as we do that. So the first test is 62. What is the weight of that test? 20%. The next test is 83. What's the weight of that test? Next test is 91. The weight is? Right. Then we have a project with 88, and the weight of that is? And then our homework is 76, and the weight of that is 50. Then we divide by the sum of the weights. So if you add all those up, we get 100. So then we can put that in our calculator. I think the top turns out to be 2060 divided by 100, or 80.6%. So the problem with these usually is trying to decide which thing goes on the denominator. If you're thinking about grades, we know all of your grades are out of 100%. Sometimes it's less obvious, so it may not be something you're as familiar with, but a lot of times I might give you some unit. So, like for instance, let me make up a problem and throw it up here for you guys to try, because I know we've had a lot of questions on this. Let's see. So, I bought 4 cookies for $1.25 each, 3 pies for $17 each, and 2 coffees for $4.30 each. What is the average cost per treat? So if I ask it like this, that unit tells us a lot. The top of my fraction should be my total cost. Per is like our divided by. Then my denominator would be what? The number of treats I bought. So we have 4 cookies that cost $1.25 each. 3 pies that cost $17 each. 2 coffees that cost $4.30 each. But when I'm dividing, am I dividing by the money or the number of items? The number of items. And then since this is money, we would probably round to 2 decimal places. So it costs about $7.25. So if you don't know what to divide by on those weighted averages, look at the units given. That will help you figure it out. Is that one okay? Let's look at number 11. So this one was my correlation coefficient. Okay. So we have a whole table we have to create if we're going to find this. And that's why on part A we did the stuff from our calculator. So look on your formula sheets first of all. Let's make sure we know how we would set this up. Okay, correlation coefficient. The very first bullet under chapter 4. And tells us R is, what does this symbol mean? The sum. We're going to add up a bunch of stuff. So we have to do the x minus the mean of x divided by standard deviation of x times the y minus the mean of y divided by standard deviation of y all over n minus 1. Alright, so we need to get these things. We need the x's, we need the y's, and then we have to do what with those things? Well, first we have to multiply them all together, right? And then we'll add it up. So those are going to be the columns of my table. We'll do our x minus the mean of x divided by standard deviation, the y minus the mean of y divided by standard deviation, and then the product of that. And we found in part A, the mean for x was 5.4. Standard deviation for x, 2.0736. Mean for y. And that was all from our calculator. So you guys have those. So then these are my order pairs. We have a 0.34, 4.6, 5.7, 7.12, and 8.14. Okay, this would be a lot of points on the test just because there's so much that has to go into it. Kind of like finding a standard deviation by hand. So we do our x value. So 3. I'm going to put it in parentheses. So I'm going to do parentheses 3 minus 5.4 divided by 2.0736. And if you do that all at once, you can do second inner, and then next time we just have to change our 3 to a 4 for the next point. Okay, and the next x value was 5. So does everybody understand how I got those for my x? Then we'll do the same thing for our y. So parenthesis 4 minus 8.6, close your parenthesis, divided by 4.2190. And you can just do second enter and change your y's. Do round accordingly, but no, every time we round it is kind of throwing off the final answer a bit. So that's why we are keeping 4 decimal places. It would be really bad if you tried to just round this to 1 or 2. It would throw things off quite a bit. And then what's the next step? Multiply. So we just take those two numbers times one another. And we get you have to be careful. Filling out this table is not the end of the problem. I know when we had our quiz and there was a standard deviation question, a lot of people, they filled out the table, but then they never finished it to find the standard deviation. So make sure you're finishing it. Or we have to add up this final column. So we're taking all of those numbers, adding them together, and dividing by n minus 1. What is n? Number of points. So we have 1, 2, 3, 4, 5. So divide by 4. So our R is 0.99445. Could you compare this to the R on your calculator? Absolutely. Will it be a perfect match? Probably not, because we rounded a lot. But it should be accurate for a few decimal places. It won't be far off. So that will be worth quite a few points on the test. Are there questions about how we got that? So then part C wants us to write the equation. So go to your formula sheet. Hardest thing, you have a formula sheet that tells you everything, but you have to know how to use it. So it tells us our equation. Second bullet right below this, y hat equals b1x plus b sub 0. And b sub 1 is r times standard deviation in y divided by standard deviation in x. So we have the r. Standard deviation in y, we had written down on part A, divided by standard deviation in x. So we have our slope. And we know y-intercept. And it tells us on our formula sheet that b sub 0 is y bar minus b sub 1 times x bar. So the mean for y was 8.6 minus the answer we just got times the mean for x, which was 5.4. Gives us negative 2.3258. So that's our actual equation. Make sure, if I do ask you to do something by hand, show me the work for how you're getting it by hand. If you just write down the final answer, I'm going to assume you just did it on the calculator. And while it's fine to use the calculator to check yourself, I want to make sure that you can read these formulas and understand how to work through them. So I want to see that work. What else do we need to talk about? Standard deviation. Look at your formula sheet. So is this a population or a sample? So it tells us that our standard deviation, and it gave two different versions of the formula. We used the first one. Okay, what does that funny looking E mean? The sum. That's why we made the table, so we could add things up. So we need x sub I minus x bar. We'll have to square them and add them all together. So we'll make a column for our x's. Then we'll do our x minus the mean. And then we will square that value. We found our mean to be what on part A? 56. So our x's. And you could put them in order or do them, oh, it doesn't really matter. So I'm just going to put them in numerical order. Did you guys do that, or did you do them in the order on the table? Okay. Do you want me to do it in order on the table? Does it bother anybody? Okay. Make sure, I think another problem I saw in the quiz, if you have repeated values, you have to put every one of those in there. So we had 3 58s. Yeah, 59. I didn't make enough. Okay. So 51 minus 56 is negative 5. Negative 5 squared is 25. 52 minus 56 is negative 4. Squared is 16. 53 minus 56 is negative 3. Squared is 9. 54 minus 56 is negative 2. Squared is 4. 56 we get zeros. 58 is 2. 3 of those. 59 minus 56 is 3, squared is 9, and 61 will give us 5, squared is 25. Okay, so now to do the formula, we're not done. We have to do the square root, add all of those up. So we are adding up this final column. So 100 divided by n minus 1. N is the number of points. We had 10 points minus 1 is 9. And so when you did that, you got 3.3333. That is the standard deviation. So the table is how we get there, but that is not the final answer. Then for part I, when it asks for the variance, that's just your standard deviation squared. So we just take that 3.3333 and square it. A common thing we've seen a lot of times, like if you round differently, if you had taken your standard deviation to 3 decimals instead of 4, you would have had a slightly different answer for your variance. All of that is fine as long as I know where your numbers are coming from. So just make sure you're showing me enough work that I can determine is your difference because you rounded this number a little to fewer decimal places, or did you actually make a mistake somewhere along the way? Let's see. When can we use the empirical rule? Has to be bell-shaped data. And it tells you that on your formula sheet. It's in bold, chapter 3, empirical rule. If the shape of the distribution is bell-shaped. If it's not bell-shaped, then what do we use? Chebyshev. Bell-shaped data. What is the best measure of central tendency? Mean. Central tendency is like the middle, so the mean. If you have bell-shaped data, what is the best measure of dispersion? Standard deviation, that's how spread. If our data is skewed, what is the best measure of dispersion? Interquartile range. What is the best measure of the central tendency? The median. So know the difference between a measure of central tendency and a measure of dispersion, and when you use either one. Okay, resistant, what does that mean?
If the product gets affected by dry state.
Right. If you throw in an outlier, an extreme point, does it change a lot? Is the mean resistant? No. my example was, I think if I gave a test and I put in a score of 0 for somebody that was absent, that drops the mean a lot. Is the median resistant? Yes. Is the mode resistant? Yeah. Is the standard deviation resistant? No. Is the range resistant? Yes. It's somewhat. Not extremely, but it's not as bad as standard deviation. Is interquartile range resistant? Yes. That's why when the data is skewed, we like the median and interquartile range because those are very resistant. The mean and standard deviation especially are not. Can you have more than one mean? Can you have more than one median? Mode? Yes. What is a mode? We haven't done that one a lot, but things that are the one that shows up the most often, and you could have a tie, so we could have multiple modes. If everything has the same average, so the same mean, how do you decide which is better if you're comparing two sets of data? Standard deviation. Do you want a big or a small standard deviation? Small. Smaller standard deviation is better. What do we call it if there's something that might be having an impact on both the response and the predictor variables? So like we've had a couple examples. There was one on here with crime rates and cell phones. I think one that I gave you in class was like ice cream sales go up when the and crime rates grow up at the same time. What is it called when something has an outside influence on both of those? A lurking variable. Something that maybe we didn't consider, but it could be affecting our data. So we can't say that one thing causes another. We can say they're related, but there could be an outside influence that's affecting them. What does it mean for a point to be influential? It changes the line of best fit a lot. Okay, any point is probably going to change it a little bit, but we're looking influential is like a drastic change in the line. Correlation coefficient. What does a strong linear relationship look like? Right. If you're looking at the residuals, you want no pattern. If you're looking at your R value, the closer it is to positive or negative 1, the better. How do we check if something is linear or not from that R value? What do we have to look at? The table 2 to see if it is bigger than the critical value. So anything else? We still have a little bit of time. I'm happy to work through something else if you have questions. So let's say I have a set of data with a mean 24 and standard deviation of 3. Nothing is known about the shape. What percent of values will fall 18 and 30? Okay, if the fact that I tell you nothing is known about the shape of our data, what does that mean? Right. You can only use the empirical rule if I've confirmed that this is bell-shaped data. So if I don't know that it's bell-shaped, I can't use it. So we know the mean is 24. Okay, so one standard deviation. What would you have to do to find that range? Add and subtract 3. So that would be from 21 to 27. Okay, if I want a second standard deviation, you add and subtract 3 again. So that would be 18 to 30, and that's what we needed. So I know this is 2 standard deviations from the mean. So Chebyshev says you do 1 minus 1 over k squared. K is the number of standard deviations. So you do 1 minus 1 over 2 squared. So you get 0.75, so 75%. If I had told you this data was bell-shaped, then what percent would fall between 18 and 30? 95%. Then you would have, if I said it's bell-shaped, you could look at the empirical rule, and it says 95% in 2 standard deviations.